So, Grayson, what I've tried to give you is both a visual and a formulaic approach. Figure out where we are. We're on Lesson 4, Part 2. Okay? We there? We're all there now? So, recall, in theory, this is review. If events are mutually exclusive, well then, or means add. Now, if you add and you don't get or, what that tells you is there must have been an overlap to subtract. We also did that in terms of a Venn diagram. We said if there's a both, then they're not mutually exclusive. If events are independent, now independent meant it didn't matter whether or not the first event occurred. That didn't affect the probability of the second event. It says this, A and B is the same as multiplying. If they're dependent, A and B is the same as A times B changes depending on whether A occurred or not. We're going to get more into this one, more in depth into that one on another date, in theory. And this is why I need to do a reboot. My pen is, thank you. Ready? Hockey. So more and more professional sports teams are starting to use analytics. You may have heard of sabermetrics. The movie Moneyball was about that. That is morphing more and more into sports. So here is one. Certainly Las Vegas uses some of this to set up their odds. Two hockey players, Sebastian and Cole, each independently, so it doesn't matter what happened. The first person's effect doesn't affect the second person. The first person's outcome doesn't affect the second person's outcome. Take a penalty shot. Sebastian has a 3/4 chance in scoring. Cole has a 3 in 5 chance in scoring. What's the probability that both score? Okay, they're both shooting. That's two events. How about we go S, not S, for Sebastian scores or misses. S is for Sebastian, not for score. And then Cole can score or miss, score or miss. Is that okay? Yeah? What's the probability that Sebastian scores? 3 out of 4. You know what? I'll change colors just to make it stand out. What's the probability he misses? Okay, you're using the complement. But this is why the complement is so handy. It really gives you lots of good information. Now, down the left-hand branch, Sebastian scored. So if Sebastian scores, what's the probability that Cole scores? You know what? Whether or not Sebastian scores doesn't affect it because it says it's independent. Anyways, what's the probability that Cole scores? What's the probability he misses? What about if Sebastian misses? What's the probability that Cole scores? Still. And? This, to me, is the best explanation for independence, the best picture. I realize independence is also, if it doesn't matter which branch you go down, you know what? The fact that the two sub-branches are identical. I've got my tree set up. What's the probability of S and C? That's both. How can I calculate that? And I'm not going to use a calculator. It's top times top over bottom times bottom. I can do that in my head. There's a 9 in 20 chance that we have to go to a second shootout if these are competing teams. There's an 11 in 20 chance that the game ends after the first round of shootouts, if it's sudden death. So you're starting to see where, oh yeah, Vegas or betting companies or professional teams, hey, they'd be very, very interested in this. Both miss. Probability of both miss. How can I calculate that? 2 out of 20. Yes, I know that's 1 out of 10, but I'll let you reduce on your calculators on your own. Don't look at the clock yet. We just started. Yeah, sure. I saw you. What time is it? This is fun math. I'm teaching you how to bet and gamble, or not, really, hopefully is what I'm teaching you. Okay? Only one of them scores. Now, when I say only one, what I really mean also is exactly one. How can I figure that out? Is that one branch, or is that more than one branch? So you know what I would do? Just go, boom, right? It's those two, right? Now, I'm, again, Brendan, not a fan of the symbols, but if you wanted to write this symbolically, you would say, what's the probability Sebastian scores and Cole misses? Or, oh, you know what? What does or mean? Plus, what's the probability that Sebastian misses and Cole scores? Oh, but if you really want it to be fancy, or is, you could use the union symbol. See, I find that yucky to keep track of. To me, the tree is visual. It's going to be, 3 out of 4 and 2 out of 5, or 1 out of 4 and 3 out of 5. No calculator. Put it down, Brennan. Can you see it's going to be out of 20? Because each fraction's out of 20. Brendan, top fraction, 3 times 2 is what? Second fraction, 1 times 3 is? 9 out of 20. Oh, you know what? The probability that they both score is identical to the probability that only one of them scores. That might be useful for betting. Oscar, what does D want? Okay. Can you calculate D without looking at the tree by looking at the previous questions that we've done? Oh, sorry, what was that? 9 out of 10. He said 9 out of 10. I was looking for 18 out of 20. Yeah, you know what? If this is both miss, the complement of both miss is at least one scores. And this is again where often you're going to find it's easier to find the complement and go 1 minus than to actually find the complete answer. So at least one of them, I'm going to go 1 minus the probability of which is 1 minus 2 out of 20. By the way, what's 1 if I write it over 20? Don't overcomplicate this. It's 20 over 20, right? This is 20 over 20. Take away 2 over 20, which is? By the way, there was somebody last day who, when they were adding fractions, was also adding the denominators. Can you see why you can't do that? Because if subtracting, you'd have on the bottom 20 minus 20. You'd have a 0 on the, well, it freaks everything out. And yeah, 9 out of 10 in lowest terms. Okay? Let's go one further. E, they each miss their first 2 shots. What branch are we down? First, second, third, or fourth if they each missed? Fourth. So we're just going to continue that branch. Sebastian hits his third. Cole misses his third. Okay, so we want to fill in Sebastian hits, Cole misses. You don't have to go in the same direction as I did, but I noticed in my tree, whenever I went to the left, that was a hit, and whenever I went to the right, that was a miss. So I thought I'd be consistent, Chelsea, just so that I don't make dumb mistakes. Okay. What's the probability that Sebastian hits? What's the probability that Cole misses? What's the probability that we have miss, miss, hit, miss? How can I calculate it?
Multiply.
Yeah, right? Multiply down. I can extend this tree as far as I want, Rachel. It gets unwieldy and cumbersome, but I can do it. So it's going to be miss and hit and miss. Put your calculator down, Mac. On the top, what's 1 times 2 times 3 times 2? What's 1 times 2? Times 3 times 2? So the top's going to be a 12. On the bottom, I see 20 times 20. What's 2 times 2? 4. What's 20 times 20? Yeah. So I'm still staring at you. 400, you say, without a hesitation? It's that. Which I guess you could divide by 4, 3 out of 100. Oh, that's actually kind of a nice. There's a 3% chance, because 3 out of 100 is 3%, that we have miss, miss, hit, miss. In other words, what's the probability that both miss and Sebastian wins in the second round? There's a 3% chance that they both miss and then Sebastian wins in the second round if it's a sudden death. Okay. Mark, you with me? Yeah, Logan needed the little dap there. That's good. Yeah. Although you could also maybe just straight to the head. No, never mind. The hand is good enough. Okay. You awake? Good? Let's turn the page. Taylor read example 3. Save it. Save it. Suppose a soccer game will be decided with a penalty kick. Okay. If both teams miss or both teams score, there's another round. Team A scores on 75%. Team B scores on 60%. What's the probability that A wins in the first round, B wins in the first round, B wins in the second round? You know what? I think this is going to be a tree. What are my events? A, hit or miss. Next level, B, hit or miss. And then I think for part C, I might have to extend it, but Mac, I'll do that later. Try drawing the tree on your own. I'll do it up here. Let's see if we get the same thing.
I just realized something.
Yo.
In example 1,
Yeah.
with E, it says they each missed their first 2 shots. We only covered it with the...
You know what? What I meant is a total of 2 shots.
Ah, okay, okay.
Yeah. You know what? You're right. I should just scribble that out, though. They each missed their first shot. Although it wouldn't be that hard to extend it one more, because then we'd have one more miss, one more miss. It'd be doable. Meanwhile, let's fill in my branches, Mr. D. I'm making an assumption here that these are independent. By the way, in real life, Dom, that might not be true. In real life, if the first team makes it, maybe there's more pressure on the second person. Maybe they're more likely to whiff. Maybe. I don't know. Is that your tree? Yes? So, if both teams miss or both teams score, there's another... Team A wins in the first round. You know what? That's that branch. Right? A scores, B misses. Yeah? Which is going to be 0.75 and 0.4. 0.75 times 0.2 would be 0.3. I'll use a calculator this time. No, do it in your head. 0.75 times 0.3?
Yep.
30% chance that Team A wins on the first round. Would you take that bet? Would you bet money that Team A wins after the first round? No. There's a 70% chance you're going to lose money. What's the probability that Team B wins in the first round? Well, that's not going to be that branch. That's going to be that branch. A misses, B scores. Do that one in your head, Mr. Dueck. Okay. 0.15?
On second thought, I'd rather bet for Team A.
Well, but even then, if you're betting on Team A in the first round, you're still more likely to lose money. I wouldn't take the bet, period. Now, if they said if Team A wins, oh, heck yeah, because Team A has a higher probability of winning, I'll take that bet every time. Yeah. By the way, in 2 lessons, I will be asking one of you to bet a toonie with me. Okay. And we'll talk about that. It's called the birthday problem. It's very cool. It's also a good way to make money for the rest of your life with a bet, because it's a very counterintuitive answer. Brianna, what's option C? Can you read that to me? Okay, second round. Ooh. How do we get to a second round? For us to get to a second round, they either both score or, what does or mean? They both miss. So I'm not going to fill in these two branches. Yeesh. We want team B to win, yeah? So we want both score, and then we want A to miss, B to win. Or they both miss, and we want A to miss, B to win. Is that okay, Jake? What's not A? 0.25. And then B is 0.6. What's not A? 0.25. And B is 0.6. There, for this particular question, Ashley, because they said we only move on if both teams make or both teams miss, it's going to be this branch or that branch. It's going to be 0.75, 0.6, 0.25, 0.6, or 0.25, 0.4, 0.25, 0.6. Did I get all my numbers right? I think, yeah? Make, miss, make. Miss, make. That's the only way B can win. This one I think you can use a calculator for. By the way, if you get an answer bigger than 1, you've screwed up, right? The answer has to be less than 100%. 0.75 times 0.6 times 0.25 times 0.6, or 0.25 times 0.4 times 0.25 times 0.6. You get 0.0825? Now, this is a very specific bet, Zach. This isn't saying what's the probability that B wins. This is saying what's the probability that B wins in the second round, not on the third round, not on the first round. So that's why it's also a pretty small number. But it's possible. There's an 8.25% chance that they win in round 2. No, the complement for C is only B doesn't win in round 2, which means could win in round 1, could win in round 3, A could win in round 1, A could win in round 2, A could win in round 3, A could win. So there's a whole bunch of possibilities. Yeah, the complement is not saying that A automatically wins. The opposite of B winning in the second round is B not winning in the second round. In fact, when we did our logic unit, it's the, not the contrapositive. I think we called it the complement. There was also, though, I think putting not in front was a logic statement as well, but I can't remember what we called that. Yeah? Example 3. Taylor, could you read example 3, please? In a nice, loud voice. Thank you. Sure.
Taylor has difficulty waking up for school on time.
I can relate. I have difficulty waking up for school on time. Who doesn't? So Taylor's a high-achieving student, and so she's come up with a solution. Keep going, girl. Keep going.
So she decides to set 3 alarms.
Oh, the dedication. Keep going.
From prior experience, she knows that it takes at least 2 alarms going off in order to wake her. Each alarm goes off independently. The probabilities that each alarm rings is 0.6, 0.8, and 0.85, respectively.
Okay. How many alarms?
3.
How many levels will my tree have? 3. It's going to be on, off, on, off, on, off. Okay, this is going to be a little unwieldy, but not. I can do this. I can do this. So let's call how about we call the alarms A1, A2, and A3? A for alarm. So it's going to look like this, Taylor. Let's draw our tree. We have A1, not A1. And I'm drawing it fairly wide because I'm remembering that I got to get 3 levels in, right? A2, not A2, A2, not A2, A3, not A3, A3, I'm already getting crowded, I should have made my tree bigger, A3. Are you seeing from just drawing this why I said 3 is about my limit for a tree? Can you imagine going one more level? It's just physically tough to draw. Okay. Taylor, let's fill in the probabilities. What did you say the probability of the first alarm going off is?
0.6.
What about not going off? Yeah. Second alarm? 0.8, 0.2, 0.8, 0.2. Third alarm? 0.85, 0.15, 0.85, 0.15, getting crowded. 0.85, 0.15, 0.85, 0.15. Okay. What's A want us to find, folks?
All three.
How? Which branch is, that's just one branch, yes? So that's going to be 0.6 and 0.8 and 0.85. This is not as high as you might think. If you multiply these together, the probability that all three ring, even though you might say, well, there's like 85% chance and 80% chance and 60, should be like in the 80s. What do you get? Sorry? 0.306, is that right? I don't think so. I think it's higher than that.
0.408.
0.408? Anybody else? Okay. So Taylor's investing in some cheap alarms. Sorry.
It's okay.
What about no alarm rings? That's the far right. That's going to be wait a minute. No, I can't just, I was going to say maybe I could subtract 3 alarms, go 1 minus, but 3 alarms is not the complement of no alarms. The complement of no alarms is at least 1. Anyways, it's going to be 0.4, 0.2, 0.15. 0.12 or 0.012? 0.012. Okay, so there's going to be some noise trying to wake her up. 98.8% of the time. I went 1 minus in my head, right? Only 1.2% of the time will her room be silent in the morning. Taylor, this is, I'm going to come back to you. C, this is what we're going to answer. What's the probability that Taylor is awakened on time? Now, what does it say the condition for you being woken up on time is? It takes at least what?
3 alarms.
Read carefully. At least.
Well, 2.
I gave you the benefit of the doubt, kid. Don't be so hard on yourself. So at least 2 means, okay, which branches? This one, yes? Is the next one at least 2? Is the next one at least 2? Is the next one at least 2? Nope. Is the next one at least 2? Yep. Is the next one at least 2? Nope. 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 It's those 4 branches. I'll see if I can fit that all in. It's a little crowded. I should have left more room, but I was trying to save paper. So it's going to be, by the way, I pick a different student every year, but the fact that you just, anyway. Okay. It was too tempting. It's going to be 0.6, 0.8, okay. 0.6, 0.8, 0.85, or careful when you walk down the branches, 0.6, because it's easy to have your eyes slip to the wrong side, 0.8, 0.15, or 0.6, 0.2, 0.85, or 0.4, 0.8, 0.85, 0.4, 0.8, 0.85. Or Did I type that right? That looks good, or that looks good, or that looks good, or I think that is. Do you get an 85% chance of her waking up? 0.854? Which is also actually higher than often I've asked kids to make a prediction, and they said, well, I mean, the best alarm only goes off 85% of the time. The probability that she gets woken up is probably going to be less than that. Actually, no. It's slightly more than the best alarm. Again, Oscar, this goes back to the very first sentence I said teaching this. All of us have a very basic innate understanding of probability, but as soon as it gets anything remotely past basic, our sense sucks. We're terrible at it. That's why we're bad gamblers. That's why we're superstitious. It's very counterintuitive. Is it 0.854? Anybody else get that? Yeah? Card questions. Card questions. I like card questions. And also I like them, I like them, I like them, I like them.
Of course, you get them on the test.
Yeah, but you know, when I'm playing cards, I'll try and play the best odds. Ty, can you read example 4 to me?
Yeah. One card.
How many cards?
One card.
How many cards? You're right.
One card.
I'm not doing a tree. I'm going to count. I think I can keep track of it up here. Keep going.
Is randomly chosen from a deck of cards. Consider the following events. H, a heart is drawn. K, a king is drawn. R, a red card is drawn.
So I wrote down here, express the following as a fraction in lowest terms, and I wrote, why no tree? Why no tree?
There's just one.
Okay. In other words, if you did a tree and you tried to multiply, you might get wonky answers, because that would actually be implying 2 cards were chosen. Okay. Remember, horizontal line or apostrophe both mean not. So this is saying, what's the probability of not H? What's the probability that you draw a heart?
13.
So what's the probability you don't get a heart? I know that reduces to 3/4, but I find that there more informative. It's saying, oh, there's 52 cards total, 39 of which aren't hearts, as opposed to 3/4, which says or implies there's 4 cards, 3 of which aren't hearts. Hearts or red? It's going to be what? Or means what? Is there overlap? Can you be a heart and a red card at this? Okay, so it's going to be, and this is about the only time that I go with the formula approach, except I'm really lazy. I'll often go H plus R minus, and I'll write the word and, because I really want to emphasize to myself that's the overlap. It's going to be 13 out of 52, or how many reds out of 52? Minus how many hearts are red at the same time? Oh, you know what? What this is really saying is, look, every single heart is in the red category, so really the probability of getting a heart or a red, same as just probably getting a red. It's half, because half the deck is red. And of those red cards, yeah, there's some hearts, but the red dominates. C. Now, I know this says and. We're not going to multiply. How many cards are we picking? 1. I'm going to count. How many kings are red? 2. Done. Right? We know the overlap. We can visualize a deck of cards. D. Ooh. Hearts and not a king. Okay. How many hearts are there? 13. Of those hearts, how many are also not kings? 12. Right? There's 1 king of hearts. And again, hopefully when you figured out the 12, you actually used a complement. Hopefully you said, oh, there's one king, so there's 12 left, instead of counting ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen. Ooh. H given R. Okay. This is going to be that. Don't write this down, just look. This is going to be probability of A given B is the probability of A and B, you can write this down, divided by the probability of the given one. Psst. What I really did is I divided this over to get that by itself. This one's written in terms of A. Get rid of that. I rewrote it in terms of B, but I remember this equation. If you give me something given something else, it's both over the given part. So you ready? This is going to be H and R, okay? What's the probability that you're a heart and a red card? How many hearts are also red? Divided by the given one. What is 13 out of 52 divided by 26 out of 52? Oh, okay, now that I see that, now Julia, this answer, here's what it's saying. If you're only picking from the red cards, what's the probability that you pick a heart? Oh, you know what? Half of the reds are hearts. Now that makes sense. I could have got there by counting, but this was complicated enough that, yay, the formula got me there too. What about red given that it's a heart? Now, so here's what this is saying. You're picking from the hearts. What's the probability that it's red? Think about it. 100%. Now let's see if we can prove it. Mathematically, that's supposed to be red and heart, which was 13 out of 52. There's 13 cards that are reds, ands, and hearts, divided by heart, which is, what's anything divided by itself? Okay, so this weird variation on the formula is convincing me, Mackenzie, that it works for questions that I didn't intuitively know the answer to, but that now I see the answer. It works for these. It's going to work for the weird stuff. We're going to spend some time with this bottom version of and. We're going to call it conditional probability. Sometimes it's called Bayes' law. And with that there, what I've written in black, I can possibly save your life. I can explain to you, any of you that are going into the legal system, why you can't ever use a lie detector in a court of law. I can sadly explain to you why racism will almost always exist. And I can probably convince you with a bit of luck why, had they had a mathematician on OJ's prosecution trial, OJ would have been in jail the first time. Preview of coming attractions. What's your homework? I have a take-home quiz for you. And then this builds on, last day I assigned some of these questions already, but you are now capable of doing all these. I don't see you for a week. I'm not really giving you homework for your long weekend. If this was a Friday, I'd feel guilty, but you got tonight and Thursday night. Get it done. You can still get your weekend off. This is going to be good to go for Wednesday. Let me give you the take-home quiz.